Hi, today we will discuss about the PLC addressing. So in the last lecture we discussed about the ladder logic programming, and in the ladder logic programming one of the most important parameter is the addressing. So whatever the instructions that we place in the program, for each and every instruction we need to address. So today we'll discuss about this addressing and its significance. So let's move on. Now coming to the addresses, there are three types of addresses. First is a physical address. The physical address, generally we address it to the physical inputs, like for a digital input, analog input, similarly digital output and analog output. So suppose if you have a module, a digital input module with 10 digital inputs, then for this 10 digital input we need to have 10 different addresses, right? Similarly, we have a memory addresses. The memory addresses are within the CPU, so we use it within the logic for internal purpose. So if you want to keep the result in some temporary space, then we use these memories. So again, this memory are of different sizes, so we will discuss about that in detail again. Next we have our special function addresses. These special function addresses, generally we use it for the timers, counters and all the special functions which are available in the PLC programming, right? So now let's move on. Now first we'll see how the Allen Bradley will follow the addressing format. So here you can see this is a format of the Allen Bradley. So here we have 6 digits. Now let's look into each and its significance. Now first one, we can see that this digit indicates whether it is an input or output. So here it is O, which means it is an output. If it is I, then it represents input. Next is the file type. This is just a numerical representation of your input and output. So 1 represents the output. Okay. Next, after the semicolon, again this digit indicates the rack number. Normally in PLC, in an industrial environment, we use the several racks. So our module or the terminal belongs to the which rack we need to specify over here. Then the next digit is the group number. In each rack there are about 0 to 7 groups. So in which group the terminal belongs to, so that will be represented by this digit. And then followed by the last digit is the terminal number. This is our terminal. So in each group there will be around 8, 16 terminals will be available. So which terminal you are connecting, that will be represented by this digit. Now we'll see this again in detail. Now I have taken an example of an address with I0:12/02, right? And this address, like from a SLC 500 PLC. SLC 500 is a large PLC in the Allen Bradley category. Now first, I, as I mentioned, I represents input, right? So this address belongs to the input terminal, that's for sure. Next, the digit 1. The 1, it's a numerical representation of your input and output. So 1 is for input. Okay, so with this 2 digits, it's confirmed that now this address belongs to the input, and here also with the numerically it is confirmed that it is for input. Now coming to the next digit, the third digit, here this 1 indicates rack number. So here you can see there are 0 to 4 racks are available. So now the current, this input belongs to the rack 1, right? Next digit, that is a group. Okay, so there are 0 to 7 groups. So this belongs to the group 2. So as of now, input, rack number 1 and group number 2, right? And the last digit is the terminal. So in this group, now here there are 0 to 16 terminals maximum. So here the 02 means it's a second terminal. Okay, now I'll show you the same with a diagrammatically. Now here a typical modular PLC will have like this. Now I have taken 3 racks. Okay, so rack 0, 1 and 2. Now here you can see the first is a power supply module, then followed by the CPU module. So as you can see, for these 3 racks there is only one CPU. Okay, and all these racks are being connected with this interfacing module. So we can call it as IM module. So now there are 0 to 7 groups, right? So you can place any of the module. You can put a digital input module or a digital output module or analog input or analog output module. So you can customize this rack as per the needs. Okay, so now I have categorized like this. So first 4 are the input modules and the last 4 are output modules. Okay, same is the case with the other racks as well. Now coming to the our address. So I is an input, which means now our terminal will definitely belongs to the first half of the module. Okay, so here I have highlighted that. So in out of any of this rack, it should be, this address, this terminal can be in any of this 3 racks. Okay, and for the next digit, it's again a numerical representation of the same. Now coming to the third digit, this is 1. So it is clearly, it's mentioning that rack 1. Okay, so rack 1 means this one. Okay, so now here is a out of this 4. Okay, so it must be in this 4 only. Okay, next coming to the group. So this belongs to the group. So here we have total 7 groups. So this is 0, 1, 2, 3. So as I mentioned, it's 2. So it means definitely it belongs to this group. Clear? Now again in this group, there will be a terminals starting from 0 to 16. So that is represented by this number, terminal number. So here is I have taken this dots. So 0, 1 and 2. So here is a terminal. Here we go. This is our terminal and its address. So this is how an Allen Bradley PLCs will follow an addressing system. Okay, same is the case with the output modules. So this is an example which is showing as a digital input. Okay, now similarly I have taken a in some RX logics there are some other way of representation. Like this is a very short representation of the address with only 3 digits. So file type, its output, then group, and then the terminal number. Okay, so now let's again look into this address. So again the typical modular concept. So with the input and output models. So as I mentioned, this is the output. So definitely it belongs to the last 4. And then coming to the group, this is belongs to the 5. And then last, it's a 0th terminal. It means the first one. Okay, so this is our terminal. Clear? So like this, we will address our input output modules in Allen Bradley PLC when we write a ladder logic. Okay. Now similarly, apart from the input and output, we have some other file types like B. B represents the binary, which is memory, we can say. Okay, and similarly we have T for the timers and C for the counters. And for T, the numerical representation is 4, and for the counters, the numerical representation is 5. So like that, the numbering system has been assigned. Okay. Now here we can see the input terminal, the physical terminal, along with the register format. Now here there are about 16, total 32 terminals. Okay, so 32 terminals are available, each with a status like on and off. Okay, now these status are being stored in a register, a 16-bit register, where each bits like 1 and 0, this binary bits represents the status of the input. Now you can see that the first terminal, it is on. Okay, this is on, and on means it is represented with 1. Then second terminal, it is represented as off, which means it is 0. So each digit represents the input, whether it is on or off. So these inputs can be a switches, a sensors, a proximity, or any field devices we can consider. Same is the case with the output as well. So here is the output register. So the PLC, after computation, has taken some decision, and that decision in the form of binary bits, and these binary bits are given to the output module. And here in the output module, as you can see, the 1, which means this particular output is triggered as on. Then 0, which means this particular output has been turned off. Okay, so all this information will get updated as per the program, as per the input condition. Okay, so it is not like that once it is turned on will remain on forever. Okay, so as per the logic, as per the input condition, after computation, this status will get updated. So how it gets updated? Here you can see in my previous video, there are 3 scans. One is the input scan, with which the inputs get updated. Next is a program scan, with which the program gets updated. And then output scan. With this, the output module, as you can see here, the outputs get updated. So now here the input 1 is on. Maybe after some time it may be turned off. So that is possible only when you perform a scan operation. This scan operation is a regular process in the PLC. So continuously this scan, periodically it will happen. Okay, so this is how we do the addressing in Allen-Bradley. Now here we have a next we will see the Siemens PLC addressing format, and I can say that this addressing format is a bit simpler when compared to the Allen-Bradley. Now here you can see Siemens will follow the octal number system. Okay, so we'll see what is that. Now coming to the digital input, here is a representation I 0.0, I 0.1, so on, like I 0.2 and so on up to I 0.7. Okay, after I 0.7, then again the series will be after I 0.7, then the next address will be I 1.0, 1.1, 1.2, 1.7. After that I 2.0, so on. Right. Coming to the digital output, Q. Instead of O, in Allen-Bradley O was the output, but in Siemens it is a Q. Q is represented as output. Again Q 0.0, so on up to Q 0.7, and next after that Q 1.0, 1.1, and so on. Like that the addressing will go on. Then coming to the analog inputs, analog output, here IW, input word. Okay, so one thing you need to remember, I and Q, this represents physical address. Okay, so same is the case with the analog output. Q means physical and W is a word. So you can see that the word, it comes only in the analog. So word is the 16-bit in size. Then we have the memories. So for bit addressing, we can use this M 0.0. One thing is very clear, that I represents input, Q represent output, and M represents memory. Okay, the first two represents the physical address, and this M represents memory address. Okay, so M 0.0, M 0.1, so on, M 0.7 followed by M 1.0, and so on. Like that the memory bits will go on. And if your data, if it is not a bit, and then we can use byte memory. So MB memory byte, and for 8-bit. If not sufficient, then you can use a memory word, which is of 16-bit. Then finally we have a memory double, okay, which is of 32-bit in size. Okay, so now these memories, depending upon the usage, if you are working with the timers and counters, then for the time you can use the memory double registers. If it is a normal the value within the 16-bit, then you can use memory word. Or else if it is just a discrete input and output, then you can use this memory as bits. Okay, so this is a Siemens addressing, and here is the formats. Okay, now let's look into this memory concept a bit in detail. As I mentioned, M0.0 is a memory bit. Okay, and this follows the octal number system, so it may go up to M0.7. There is no M0.8, M0.7. After that M1.0. Now this M0.0 to M0.7, which forms 8 bits, and these 8 bits together can be used as 1 MB, 1 megabyte, and it is represented with 0. MB0. MB0 will consist of 8 individual bits, that is M0.0 to M0.7. Okay. Similarly, the next after this M0.7 is M1.0, so on up to M1.7. The another 8 bits. The another 8 bits, again, it is represented as MB1. Okay, this MB1 register consists of M1.0 to M1.7 bits. MB0 consists of M0.0 to M0.7 bits. Right. Now, like that, we can have memory byte register MB0, MB1, MB2, and so on. MB2, you can guess, MB2 consists of MB2 will have registers starting from M2.0 to M2.7. Understood? Next, what if we combine MB0 and MB1? If we combine MB0, you know that this is the 8-bit, and I have shown all this 8. This is also another 8-bit. So if we combine MB0 and MB1, it becomes a 16-bit register, which is called MW, memory word. This is a 16-bit. Okay, so MW0 consists of MB0 and MB1. Again, MB0 consists of M0.0 to M up to M1.7. This register can accommodate M0.0 to M1.7, total 16 bits. Okay. Then, what about MW3? I mean, you can have MW0, MW1, MW2, and MW3, and so on. Okay. So each is of 16-bit. So if you combine this any two word registers, then it becomes a MD0. Okay, it becomes a MD0. So MD0 will have a total, it's a 32-bit in size. It consists of MW0 and MW2. Okay, and this MW0 again consists of MB0 and MB1, 8-bit each. Then again this MW2 consists of MB2 and MB3. Okay, so this is of again 8-bit. So total it's a of 32-bit in size. Okay, so this is a memory double register. Mostly we use it for the timers, counters, and so on. MW registers for normal any numerical operations, we can use of this. Similarly, MB byte registers, and these registers for the digital input and digital output. Okay, so this is the addressing of the PLC. So thanks for listening. Hope you understood.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.